acknowledge my faculty colleagues at UAB, my research staff, postdocs, and these graduate students who have contributed to various aspects of the research which I'll be talking about. So here is outline of the presentation. I'll be talking about 4 topics, all related to microwave plasma processing. The first one is going to be a homoepitaxial diamond growth. So I'll pick up one application of a diamond encapsulated sensors for extreme environments. The second topic would be nanocrystalline diamond deposition on metals. And I'll pick up one application on wear-resistant biomedical implants. In the third topic, we'll be talking about the novel superhard materials based on carbon, nitrogen, oxygen, boron, SNOB materials, particularly for their application as ultra-high temperature ceramics. And then the last topic I'll be touching on will be the machine learning enabled material discovery and how that would open up a microwave plasma synthesis of novel materials. So just a general introduction about plasma-based methods for material deposition. Plasmas are, of course, weakly ionized gases consisting of collection of electrons, ion, neutrals, and reactive molecular species. And for our talk today, the most important aspect is the reactive molecular species, which, of course, react at the surface of the substrate to produce new materials. The plasma densities we'll be talking about typically range from 10 to the 8 per cc to about 10 to the 14. And these are the plasma density used in plasma synthesis and processing. And keep in mind that these are non-equilibrium plasma. The electron energies are much higher, like few electron volt, while the ion energies are of only few tenths of an eV in a plasma deposition process. So this basically lays out all the essential elements in the plasma synthesis and processing of materials. You have modeling and simulation, novel plasma reactor design, plasma diagnostics and control. And the names you see are basically the various academic institutions in Alabama involved in various aspects of this research. So this is a statewide program in Alabama. So all these 3 things combine into this plasma processing and synthesis of materials. And they, of course, cover a wide gamut of applications in aerospace, agriculture, biomedical, and manufacturing. Okay, so let me start off with the first topic, and that is diamond sensors for extreme environment. And the important point here is that we are developing sensors which will operate in high pressure, high and low temperature, corrosive, and high radiation environment. So the basic idea here is that you use your microlithography facility. This is a maskless lithography facility at UAB, along with sputter deposition of metals on diamond. And then you can microfabricate different sensors on top of a diamond substrate. So here, for example, I show an electrical 8-probe design, and then here we show a loop, which is like a magnetic pickup coil. So once you fabricate these using microlithography, what we do is we encapsulate them in a homoepitaxial CVD diamond layer to harden these sensors for use in extreme environment. So for that, we took these microfabricated sensors on top of the diamond into a microwave plasma CVD reactor at UAB. This is a 2 kilowatt system, basically dedicated to diamond-based sensors and nanocrystalline diamond films. So this is a live shot of a diamond with sensors actually in a plasma. Typical deposition temperatures are around 1200 degrees Celsius. And we have developed a specialized growth chemistry involving hydrogen, methane, nitrogen, and oxygen. And this growth chemistry is essential in actually doing a fast homoepitaxial diamond deposition to encapsulate the sensors. So this slide shows the typical processing steps. So for example, if you start with the lower left hand here, so you see a diamond anvil with these 6 probes, microlithography deposited. This is looking it from the top. And you see right now these probes are connected here. And then once you do the CVD homoepitaxial deposition, you see that this circular culate of the diamond actually is converted into a square due to the homoepitaxial diamond growth. And then you polish this and expose these probes as you see these shining probes coming out of the diamond to make electrical contact with the sample. And here is another example of a magnetic pickup coil on top of the diamond. And then this is after encapsulation of that coil in the CVD diamond. So I'm going to show you just one example of this diamond with embedded sensors in an application involving very high pressures. So what we have here in the left panel is the electrical resistance, 4-probe electrical resistance of the sample as you apply, and this is a function of time. And the pressure is building up also as a function of time. You see this blue curve, and you see that the resistivity drops by several order of magnitude as gallium arsenide goes from semiconductor to a metal transition. And when you release the pressure, the material goes back to the semiconducting state. The important thing here is also that we have demonstrated the wireless capability of this diamond sensor by reading this on your laptop or on a handheld device, the voltage on the sample as a function of time, showing these 2 transitions. Now, moving on to my second topic, and that is nanocrystalline diamond. And here I just show you a very interesting example of plasma chemistry changing the morphology of diamond from a microcrystalline, well-faceted to a nanocrystalline diamond. And you can see from application point of view, you have a very rough surface here, 270 nanometers, and then here, it's a very smooth surface. So this is what a nanocrystalline diamond looks like in the SEM, scanning electron micrograph. And this again is driven by a special chemistry in the plasma. Now, further fine-tuning the plasma chemistry, you can what we call as ultra-smooth nanostructured diamond, USND, on titanium alloy. You can get the grain size of diamond as low as about 6 nanometers in the film. So from application standpoint of view, if you put this nanostructured diamond on, let's say, the aerospace and a biomedical implant alloy like Ti6 aluminum 4 vanadium, and then you do indentation testing to really find out the adhesion of these nanostructured diamond coating on metals. And here is a pictorial representation with the increasing load. You can see as you go to higher load on this ball indenter, you make a bigger impression, but the film never delaminates. In fact, it shows really a very interesting behavior of actually micro-cracking, which is a characteristic of not a brittle failure, but a plastic deformation zone. So we were encouraged by these adhesion tests. So then we looked at this as an application for wear-resistant coating on biomedical implants. So this is actually a knee implant which has been coated with the nanostructured diamond. And what we have done here is that we have a knee simulator where we look at the wear of this nanostructured diamond coated knee implant against ultra high molecular weight polyethylene, which is the standard application as the device is implanted in the human body. So what it shows is that even after 1.6 million cycle, there is no wear of nanostructured diamond observed on the surface. So this one really looks promising in general for biomedical implants. So now I'm going to go to my third topic area and talk about materials beyond diamond. The reason why we look for materials beyond diamond is demand for ultra hard materials at high temperatures in an oxidizing environment. As we all know that the diamond, when heated in air, start oxidizing around 600, 800 degrees Celsius. So it's not useful for high temperature applications, as well as in machining of ferrous alloys where you have chemical reaction between diamond and these ferrous metals. So we focused our attention on carbon, nitrogen, oxygen, boron materials. This part of the periodic table we call SNOB. And there are some very exotic materials which have been predicted over time, and some of them have been realized, but not all by plasma methods. So this is another look at how to really visualize this in form of a tetrahedra. So you have a carbon in the middle, oxygen, boron, and nitrogen, and I have noted down some of the Superhard compounds here. But in today's talk, I'm really going to focus mainly on this axis, boron-carbon axis, and some future work in the ternary BCN material. So we are going to examine first what happens if we add boron to the diamond, and then go eventually to very high boron content materials. And this is a 6 kilowatt system, which is a bigger version of what you saw earlier for diamond sensors application. This is can deposit diamond onto about 4-inch diameter substrates. So it's good to make connection with what we talked about nanocrystalline diamond. So this is our standard nanostructured diamond, which I described earlier. And what happens if we add boron in the plasma? We found something very interesting, that when you add boron, you actually go back, and it's doing reverse of what nitrogen was doing. It goes back to the microcrystalline diamond. So we were intrigued by this. So this is kind of X-ray diffraction pattern of these 3 samples. So you have microcrystalline diamond, obviously nanostructured diamond shows a broad 111 peak of diamond. And then we have this B and D, which is basically boron nitrogen diamond, which is here. And as you can see that the peak is shifted to the left, and that is because as you add boron to the diamond lattice, your lattice parameter increases. So that's where the peak is shifted. So now going higher in the boron, along the boron-carbon axis. So this is the material which has been predicted by Dr. Cheng-Chien Chen at UAB, which is a BC5. And this is an X-ray diffraction pattern of BC5 in blue. And this is the structure of BC5. And the red one is, of course, just a pure diamond. So, and this is very interesting. This is phonon or thermal, the vibration calculation, the phonon spectrum. And this is on the right side is the number of vibrational modes. In these, comparing red is diamond and blue is this BC5, you can see that the phonon spectrum is shifted downwards, and as is expected because of heavier mass of boron and as well as increase in the bond length. So, so what do we find experimentally when we look for BC5 in the laboratory by microwave plasma chemical deposition? So we basically made two different materials, which is one which is a hard material with hardness of 62 gigapascal. One is a soft material with a hardness of 8 GPa. And you can see that they have a very different morphology. And this is the phonon spectrum measured by Raman spectroscopy in the laboratory. And you see the soft phase has, some graphitic peaks, but the hard phase spectrum look very similar to what has been predicted by theory. And then we have done X-ray photoelectron spectroscopy to see how much boron actually is there in the diamond lattice. And what we find is it's around 2.9 in the case of soft material, but about 7.7 in the case of hard material. So when we do XRD, what we really find is that the structure is still cubic. So we don't see BC5, but what we really see is a very heavily doped diamond material, which has about 7 atomic percent boron in it. And now we have actually extended this work to now I'm going to move completely up to the boron-rich materials. So we have this prediction of B50C2 by theory. And there is a structure which is proposed, which is stable. And we have been able to synthesize this material by microwave plasma CVD in the laboratory. And you see we get very nice crystal of this material, B50C2, hardness of about 37 gigapascals, and a very good agreement between theory and experiment. So we have kind of extended this work to produce more like a disordered BCN material because that has a better surface roughness property. So we have been able to produce a disordered version of B50C2, which may have better application in wear resistant cases where you need the wear resistance of the. So the last topic is talking about this ternary compounds. So the density functional theory calculation, which I described earlier, are very expensive computationally. So we have now looked into a machine learning model, which looks at more than 10,000 compounds, look at their elemental properties, their bonding, their orbital occupation, and try to predict what are the novel materials which can happen. So this is a bulk modulus, shear modulus, and I like to point out that these are the 3 materials which have been predicted now for hardness ranging from 49 to 75 gigapascals. Now, once we do a pilot studies like I have been describing of material synthesis, eventually you want to scale up for manufacturing. So here we have built a large area system. You can see 30 centimeter by 30 centimeter. This is based on a microwave array technology, which can be scaled up even more. And we have these unique design of having these 24 gas inlet for reactive gases to assume uniform deposition. So this has been operational at the University of Alabama, Birmingham. We have success in depositing a sp3 bonded carbon with this system. And then we have online optical emission spectroscopy system integrated to achieve online process control. So to summarize, these four areas. So I have discussed with you today the wireless capability for diamond-based sensors, which will enable remote sensing in extreme condition of pressure, temperature, radiation, and corrosive environment. The nanocrystalline diamond coating on metals have promising application as wear-resistant materials in biomedical implants. So machine learning enabled discovery of novel materials, I think, will lead to synthesis of ultra-hard, high-temperature ceramics. And then the large area microwave plasma chemical vapor deposition system has been developed for scale-up synthesis of novel material. So that concludes my presentation.